learned, could you please come up to the blackboard and write any one of one to four Maxwell's equations as we've learned them so far. Try to write down the simplest one. Try to write down the one that we learned earlier on. The one that we learned first. Alright. That's not right. Could you come to the blackboard, please? Try to write on the first one that we learned. What about the vector signs? What does this dot represent? Alright, and what kind of area is this? This is a closed area. So this is one of the four Maxwell's equations. It's called the Gauss's law. It tells you that around the closed area, surface area, the dot product of the electric field and the local area vector is the charge enclosed inside the volume that is bound by that surface divided by epsilon naught. This is the first Maxwell's equation, which is called the Gauss's law. Could you come to the blackboard, please, and write on the second one, another one here. If I replace this electric field with the magnetic field, what happens? That's not possible. Can anyone try to write down the four Maxwell's equations? Could you give it a shot? The equations as we've learned them so far. Up. आप आए इधर लिख के दिखाएं. Where are the vector signs? What kind of area is this? Alright. So what law is this? Just hold on. What law is this? कौन सी Maxwell's equation? No, this is Gauss's law for magnetism. This is Gauss's law for charges. Gauss's law for electricity. This is Gauss's law for magnetism. What does this law imply? Magnetic field zero नहीं होती. No. This shows us that the flux due to the magnetic field through a surface is zero. The dot product of the magnetic field with the local area vectors integrated over a closed surface is zero, which means that the magnetic flux through a closed surface is zero. This is Gauss's law for magnetism. It means that the magnetic field lines have to be continuous. They have to be continuous. They cannot start and stop like electric charges or electric fields do, because there are no magnetic monopoles. So this is Gauss's law for magnetism. Now a third law. Right. So this, what law is this called? It's called Ampere's law. And this is a closed path. This is a closed loop on a surface. It's not a surface, it's a path on a surface. And this equals mu naught times the current that pierces that surface which is bound by the path. This is called Ampere's law. And this is, thank you very much. This is the fourth Maxwell's equation. You can put them in any order you like. This is called Faraday's law, but it's a partial form of Faraday's law. This is called Ampere's law. This is a partial form of Ampere's law. Now, let me give you a lightning introduction or a lightning review of these four equations. I've already spoken quite a bit about this, but let me gather things together. E dotted with dA over a closed surface area equals the charge enclosed by that area divided by epsilon naught. This charge is resident in a volume, and this area, this closed surface area, is the outer periphery of that volume. So I have a volume. This is three-dimensional, and on the surface of this volume there is a surface which is closed, like the surface of a balloon. Inside the balloon we have air. Air forms a volume. So the total electric flux through this surface, which is just the left-hand side of this equation, equals the charge that is enclosed within the volume divided by epsilon naught. This is Gauss's law for electricity. The second law that we've seen is that if we were to repeat the same thing for magnetic fields, B dotted with dA over a closed surface equals 0. So flux, magnetic flux can penetrate to the surface, but the amount of flux entering the surface has to equal the amount of flux leaving the surface, because there is no such thing as a magnetic monopole. Magnetic field lines cannot start and stop anywhere. They are continuous. They cannot have sinks or sources. There can be no whirlpools where water is just sucked in and it just disappears. Magnetic field lines have to be continuous. So if you take a closed surface, the flux entering the surface has to be equal to the flux leaving the surface. No doubt, if you have an open surface like this is just an open surface which is not closed upon itself. You can have a non-zero flux through that surface, but it's not a closed surface. Clearly, if you have a surface of this kind and you have a magnetic field that is piercing the surface, the flux to this surface is non-zero, but it's not a closed surface. So this is Gauss's law for electricity, Gauss's law for magnetism. And we've also seen a partial form of the Faraday's law, E dotted with dl over a closed path, which is just line integral, equals 0. And for the same reason, we cannot have curly electric fields or electric fields of this kind. These electric fields are impossible to achieve in the limited scenarios that we've seen so far. We cannot have an electric field like this, because if we were to have an electric field like this, we place a charge here, its positive charge will accelerate as it goes around this complete circuit. So its energy is continuously being boosted as it traverses a closed path, but that's impossible. Otherwise you'll have a perpetual motion machine. So conservation of energy does not allow us to have a scenario like this. In other words, if you were to start from point A, we go to point B, to point C, and we go back to A, the potential change or the potential difference around this closed path has to be 0. We take any closed path that we like, any tortuous path, E dotted with dl about this path has to be 0. This is a partial form of Faraday's law. And lately we've also discovered the fourth Maxwell's equation, one of the four equations, and that just replaces the electric field with a magnetic field. This is again a closed path in space. This equals mu naught times the current enclosed. Now for the current enclosed, I can also write J dotted with dA, where J is the current density. Remember, this is an open path. An open area. So what this means is that if I have a loop inside space and I traverse this loop, and around this loop, if I take this line integral, which is I take the B at each point, B1, P2, I take the local magnetic fields at each one of the points on the path and I integrate. This must equal mu naught times the current that is piercing this surface. And this is an open surface, by the way, it's not a closed surface. So the total current that is coming out or into this surface times mu naught gives me B dotted dl around this closed path. This is Ampere's law. So these are the four equations that we've seen so far. Ampere's law. But remember, this is a partial form of Ampere's law. Because what we've seen so far are only static electric and magnetic fields. So far we've seen only static fields. The fields do not change with time, which means that the derivative of the electric field with time is zero. This also means that the derivative of the magnetic field with time is also zero. No doubt we can have moving charges. That's what constitutes a current. So if I have a wire and a current flows through this wire, there is some current density to this wire. It really means that charges are flowing through this wire. And if this is a metal, electrons are flowing through this wire and they're moving with a velocity called the drift velocity. So electrons are flowing through this wire with a drift velocity, Vd. And this drift velocity is the result, or this current density is the result of an electric field, E, inside the wire. This electric field causes charges to flow, but this electric field doesn't change with time. It's a DC current, it's a steady current. The transients have died out, they have withered away, and we left with a constant current. The fields can be inhomogeneous, they can be non-uniform, but so far we've only dealt with static fields, fields that do not change with time. Are you with me on this, on all of these points? The fields can be non-uniform, we've discussed non-uniform fields all throughout this course, but so far we've only looked at fields that don't change with time, they're static fields, such as DC currents, DC fields, etc. However, the moment we introduce time-varying fields, the picture here on the right-hand side of this bisector that I've drawn on the blackboard changes. These equations pick up additional terms. So these are only partially correct forms of Maxwell's equations. They're incomplete. They are complete to the extent that we only deal with static fields. But the moment we introduce time variation in the fields, do these equations change? And they pick up additional terms. Now, what I'm going to talk about first is time-varying magnetic fields. Alright. Now suppose I have a solenoid. This solenoid carries a current I. I know that the field, the magnetic field, only exists inside the solenoid. So this field is B It's a long solenoid, so the field does not go out of the solenoid. It's long, slender, and the field is approximately uniform inside the solenoid. What is the amount of this field? What is B naught or B? What does this equal to for a solenoid? It's mu naught, the number of turns per unit length, into I. Now outside this solenoid, is there some, in the ideal conditions, is there some field outside the solenoid? Zero. It's totally zero. So B outside is zero. The electric field outside is also zero. There's no electric field that comes out of this solenoid. Alright. If we really ignore the surface charges. Now I would like to look at this solenoid from a different perspective. I would like to place my eye here. So I'm now looking at a cross section of the solenoid. So if I look at the cross section of the solenoid, this is what I will observe. There are loops of wire. And the solenoid is carrying a circulating current. So I'm looking at the solenoid head on. The current is circulating in, say, an anti-clockwise sense when I observe from the right. Now this produces a magnetic field. What's the direction of this magnetic field? It's pointing out of the plane of the blackboard. So this B is pointing out of the plane of the blackboard. It's mu naught n I, say some unit vector k. If I define my axes like this is x, y and z. So z is coming out of the plane of the blackboard, so this is the direction of the magnetic field coming out. Now there's no magnetic field outside because it's a long slender solenoid. There's no electric field outside. Now what's going to happen if this current is static? Nothing changes. Remember that this current is flowing inside the wire because of electric fields that have been set up in the wire. Right? Just remember that. Now if nothing changes, there's no field outside, there's no current outside. So if I place a charge here, say a test charge Q outside the solenoid, nothing's going to happen to it because it doesn't see any electric or magnetic field. Remember that if it sees an electric field, it's going to accelerate, it's going to experience a force. Will it experience a force if it sees a magnetic field? Only if it's moving, only if it has some velocity, because of the Lorentz force. Now what if this current, which is circulating inside the solenoid, changes with time? So if I were to make a plot of how the current changes with time, suppose up to a point t naught, the current is just constant. So the field inside is constant and there is no field outside. Neither magnetic field nor electric field. Now if the current suddenly ramps up at point t naught, which means that di by dt, which is the slope of the current, is positive, the current goes up. This is positive, means that the current is increasing. Now this current is increasing. What's going to happen to the magnetic field inside? If I make a plot of the magnetic field inside, what's going to happen to this field? It's going to go up. And it's going to go up at the same rate. So up till point t naught, the field is constant at mu naught ni. Then it's going to go up. And the slope of this line is represented as dB by dt, which is mu naught n di by dt. So the slope of this line is going to take up this value. It depends upon the slope of the current. How much are you ramping the current? So you ramp up the current, the field inside goes up. But will there be any magnetic field leaking outside? There will still be zero magnetic field outside because the magnetic field is confined to within the axis of the solenoid, of long slender solenoid. So there is no magnetic field outside. But lo and behold, what you really observe is something quite interesting. If this field goes up, we have a changing magnetic field. This charge starts to accelerate. It's outside the solenoid, it doesn't see any magnetic field, but it starts to accelerate. Okay, and let me tell you what the direction is. So if this field goes up, this charge, if it's a positive charge, it's going to experience a force due to which it will accelerate in this direction. And it will start circular motion. Now this charge is outside the solenoid, it doesn't experience a magnetic field, so it must experience an electric field. That electric field that it experiences, if it's E, the force that this charge is going to experience is Q times E. Now look at this electric field. Now this is an experimental observation, it's an empirical observation which was first discovered by Faraday. Now if this charge is outside the solenoid, it's going to experience a force, and if you look at the direction of this force, which is also the direction of the electric field, then this force is going to point, or electric field is going to be tangential to the imaginary circle that I've drawn here. Now this electric field is produced due to a changing magnetic field. In this region, before time t0, there is no electric field outside. So if I plot the electric field on this graph in blue, up till about time t0, there is no electric field outside the solenoid. The moment you change the current is the moment you change the magnetic field. Does an electric field pop up. It comes out of seemingly nowhere. That electric field is proportional to the rate of change of magnetic field, and is proportional to the rate of change of current. If this is constant, because this slope is constant, this electric field just takes up a constant value after time t0. The moment you turn off the change in the current, which means that the magnetic field remains constant, this electric field drops down to 0. So this electric field, which is tangential, only exists at the point where the magnetic field inside the solenoid is changing. Alright? Now this electric field is not produced by charges. So far, we've seen electric fields that are produced by charges. For example, we have, say, some distribution of charges, like an electric dipole. It produces an electric field. We have a surface which is charged, uniformly charged. It produces an electric field. We have current flowing through a conductor. That is really means that there is an electric field inside this conductor, and that electric field has been produced by a gradient of charges. So far what we've seen is that electric fields have been produced by gradients of charges or by charges or static charges. But here there are no charges anywhere. There are no free charges anywhere inside this circuit, inside this diagram. There could be small surface charges on the surface, but those are immaterial, they are really small. These electric fields can be really large, and they are not produced by any Coulombic charges. So that's why this electric field is generally denoted by the subscript NC, which means non-Coulombic electric field. And it also stands for non-conservative. I will explain what non-conservative means. So it's a lucky stroke of fortune that NC stands for non-coulombic and non-conservative at the same time. So this electric field is produced because of the changing magnetic flux through the surface. Now, what this also means is that this equation that we have here has to be modified. Because if you look at this path, if you start from point A, go to point B, go to point C and come back to A, then the electric field is always tangential and the direction of traversal of this path is also tangential. So this integral is non-zero. Therefore this right hand side is different from zero. So what Faraday proposed because of his experimental observations is that for time varying magnetic fields, Faraday's laws as we've written them in the partially correct form, particularly this equation, is changing. So if you now integrate over a closed path the electric field, this electric field can have a coulombic component and it can have a non-coulombic component. About a closed path, but we know that the dot product of the coulombic component over the closed path is zero, and this non-coulombic component can be non-zero about the closed path. So this thing is zero. So what we really have is if we put coulombic electric fields here, electric fields that are due to charge distributions, does the line integral turn out to be zero? But if we have a situation like this in which there are changing magnetic fields, then this line integral is not really zero. This line integral turns out to be equal to the rate at which the flux through the surface which is bound by that path changes. d by dt over the flux through this surface. The rate of change of magnetic flux, by the way, Fm. And I put a minus sign here as well for reasons that I'll explain in a minute. Okay. Let me write down this equation once again, and then you take a deep breath, and then I'll explain what it means. This Faraday's law has to be modified if we were to take into account time varying magnetic fields. And how does it modify? The line integral of the total electric field over a closed path must equal minus the time derivative of the flux through the surface, which surface I'm going to explain. And this magnetic flux is nothing but the integral of B with the local area vector. This is an open surface. This is the final glorified form of Faraday's equation, which is one of Maxwell's 4 equations. Now I give you half a minute to write this down in your notebooks, to think about this, and then I'll explain what all of this is meaning. And why do we have a minus sign here, and what does it imply? Abhi pehle, जी? नहीं, वो एक्सेलरेट करेगा, लेकिन फील्ड भी तो वेरी हो रही है. So the current is varying, which means that the battery is supplying energy. Energy has to always needs to be conserved. Okay, think about this for a minute, and then I'll explain what all of this is meaning. what this means. You already partially know what this means, but let me invoke the right hand side and an explanation of the right hand side by bringing to attention the Ampere's law, because this is something you've already seen. Okay? So in Ampere's law, if I have a loop and I would like to find B dotted with DL around this loop, this is a closed loop, right? This equals mu naught times the current enclosed by this loop, which means you take the area inside the loop, and it's an open area now because it's a two-dimensional surface, you've drawn a loop on it. Inside the loop there's an area. This is just like a soap film. This is the outer periphery of the film, and this is soap inside. Okay? So this is an area, an open area on whose outer periphery lies this path over which you're integrating the magnetic field. So you find the current through this path. Now if you have a wire, and this wire is carrying a current I. And this wire is at right angles with respect to this area. Remember, its area is always a vector. So this area vector will have a direction A or dA for this small point. If this current carrying loop is normal to this area, so you take all of this, all of the current I, right? Because the current that pierces this area is I. However, what would the situation be if you have a current carrying loop that is now tilted at some angle with respect to this surface area? What you really need to do in this case is you'll have to replace this I by J dotted with dA. Okay, what does this mean? I have a loop and inside this loop I have a wire which is carrying a uniform current density. Suppose that current density is like this. So the current density vectors are all normal to the loop. So they are parallel with the surface area. So if I integrate this J with the small area vectors, so the area vectors are all normal to this loop, right? This is the direction of each area vector, dA. So you have a loop and you break that loop into small sections like this. Each small section will have a small area vector dA that is normal to the loop. Now you would like to find the right hand side of Ampere's law, and you would like to find out the current that pierces this area. So what you would do, you would take this area, break up it up into small sections, find the infinitesimal area vector for each section, and then locally take the dot product of the current density at each of these sections and then integrate. So here the current density is zero everywhere here. It's zero everywhere here because the current is actually flowing through a small conduit or a wire. It's flowing through this wire and there is no current here. There is no flow of charge in this region because this wire is a thin wire. So current is only flowing through a small section of the loop. So the local dot product everywhere here is zero. Here it's zero because J is zero everywhere here. J is 0 here, J is 0 here. So if you take the local dot product, it's going to be 0 anyway. In this particular case, inside the wire, the J vectors are non-zero because there is a flow of current. So you take the dot product of the J with the area vector here, both of them are parallel. So you take the dot product here, you take the dot product on this section of the wire, and this is going to be non-zero. If you take the dot product, locally J dotted with dA, both of them are parallel, so you can just take JDA. The angle between these local vectors is 0, so cosine of 0 is 1. And then if I integrate, this simply gives me the total current through this area. So the total current through this area is simply J dotted with dA. And this situation can be generalized. If you have a loop like this and you would like to find out V dotted with dL about this loop, this will give you the left hand side of Ampere's law. Now you would like to find mu naught times the current enclosed. Suppose the current enclosed is now like this, which means that the wire is slanted and is making a certain angle with respect to the surface of this loop. Now the current density vectors are pointing like this. The current density here is 0, here it's 0. So if you would like to find the total current that pierces this area, you will have to use this expression J dotted with dA. But J dotted with dA equals, in this particular case, J cosine of theta dA. Now if this area is, let's look at this area here. This small circular area is dA. And dA cosine theta is a particular projection of this area. That projection is simply this projection, which is normal to the flow of current. So this area is going to be dA cosine theta. So this normal area is dA dash. So instead of cosine theta dA, you can put dA dash. But this is simply the current that flows through the circuit, through this wire. In other words, what you're doing in Ampere's law is you're finding the line integral of the magnetic field and you're finding the current that pierces that area. So the current is producing a magnetic field here.
The angle will be 90 minus theta or theta?
Which angle?
The angle between dA and J.
This angle is actually, if I define this angle to be theta, this will have a sine theta here. So let's define this to be 90 minus theta. Good. Because the area vector is like this. So this angle is theta. Good, thank you very much. Alright. So what we have in Ampere's law is whenever you have a current through a loop, the current actually flows through an area. Outside that area you can have a loop. The line integral of the magnetic field around that loop equals the current that pierces the area. If I have a wire like this, which is carrying current, and my loop is like this, of course B dotted dL around this loop is going to be I. It's going to be equal to mu naught I because of Ampere's law. If my loop is like this, what is B dot dL about this loop going to be equal to? 0, because you have plus I and minus I piercing the area. That area is given by whatever is inside this loop. So there is positive current that is piercing this loop here, and there is negative current that is piercing this area here. If I make a path like this that is outside the current carrying loop, what is B dot dL across this loop? 0, because there is no current that pierces the area on whose outer boundary lies this loop. So current is now producing a magnetic field. This is what Ampere's law tells us. What Faraday's law tells us is that an electric field can also be produced. Remember that if I have a wire which is carrying a current, a steady current, then the magnetic field around this wire is going to be tangential. It's going to go around like this. It's going to be curly, in other words. This is Ampere's law. What Faraday's law is going to tell us is that you can have curly electric fields as well. Remember, this thing is non-zero, and it implies that the electric field is always tangential along this path. So if I move around a closed path, the electric field and the displacement vectors are all parallel, so the electric field is curly. And who is producing this curly electric field? It's a non-Coulombic field, remember. It's not rising out of charges or fixed charges. It's coming out of changing fluxes. And fluxes through what? You always need to define an area to define a flux. What's the flux through an area? Remember, the field is a local concept. It's defined at points, but flux is through a surface. So changing flux through what? Changing flux through a surface. And what is that surface? That surface is on the inside of the loop, about which we're calculating the line integral of the electric field. So a current produces a curly magnetic field. A changing magnetic flux or a changing magnetic field can produce a curly electric field. So this is the correspondence. If I have a changing magnetic field, suppose I have a magnetic field that is changing in this direction, which means that time t equals 0, this is the field, and at time t plus delta t, the field has gone up. It's still pointing in the same direction, but now if I were to make a loop around this changing field, since the field is changing, I will produce a curly electric field. And I need to know the direction of that curly electric field. If the flux is increasing in the upward direction, then the electric field will be in such a direction so that if it were to cause a flow of charges, it produces another magnetic field that is opposite to the chain that is creating the current in the first place. I'll explain that in a minute, so don't worry. So if this flux is increasing in the upward direction, a magnetic field has to be produced in the downward direction, and that means that an electric field is going to be produced like this. If you view from the top, this electric field is clockwise. So a curly electric field is being produced. Now the point is that I will explain all of this with plenty of examples, so don't you worry at all. What the take-home message right now is that this is the Faraday's equation. It tells us that the electric field's line integral over a closed path equals the negative of the rate of change of flux through that area. Now, before I look at different interpretations, different ramifications, or different results that stem out of this beautiful equation, I would like to show you two demonstrations. And with the results of those demonstrations, you can actually appreciate the mathematics. Okay, so I turn on this projector. First off, Pelly will be on. Alright, so in the first demonstration, what I have is थोड़ा सा जरा नीचे और मैं जरा लाइट्स ऑन. Alright, so what you see here is, this is a rotating disc. This is a platter that can rotate. On top of this platter I have a magnet. And I have three kinds of sensors that are mounted on top of this magnet, or on top of, with the help of strands. Now on this probe I have a small sensor that is called a Hall sensor. This Hall sensor detects magnetic fields. Okay. Of course this magnet will produce a magnetic field. If it's just lying there perched static, it's going to produce a magnetic field. It's like a giant dipole. No flux is changing, it just produces a flux. Flux through something, through an area is just constant. Now this is a solenoid. This is a coil of wire. That's not connected to a battery. This is another coil of wire of a different cross-sectional area, different number of turns perhaps. Alright. Now what I'm trying to do is, I've connected this to a voltmeter. Now the voltmeter is slightly sophisticated. It's a computer controlled card that takes in voltages into the computer. It's a data acquisition card. This solenoid is also connected to another voltmeter, which is a data acquisition card. It takes data into the computer. Alright. So what I'm trying to do now is, I'm going to rotate this platter. And what I have is, I've written a code, a computer code that reads in the voltages. So here on the screen you can see, so this is data from the previous run. You can see three graphs here. The top graph represents voltage from one of the solenoids. This middle graph represents voltages from the other solenoid. And this represents the magnetic field that is detected by the Hall sensor. Okay, so what I'm trying to do now is, what I will do is that I'm going to rotate this platter, I'm going to rotate the disc so that this magnet now passes through the solenoid, the Hall sensor and the other solenoid. Okay? Now when this magnet passes through these solenoids, of course the magnet has a flux. It produces a field. Now that field pierces the cross-sectional area of these solenoids. And as it moves, it has a certain angular velocity. As it moves, it's going to change the flux that pierces the solenoid. And an EMF or a non-conservative electric field is going to be produced inside the solenoid. Ali तुम चलाना अगर ये चलता तो ठीक है नहीं तो कोई बात नहीं इस पे कोशिश करो चलो हैं all right, so I'm going to rotate this and I'm also going to save the data. So what I'm trying to do now, I'm rotating this platter, so I'm rotating the magnet and I turn on the acquisition. Here on the top graph you can actually see a voltage that is being developed across one of the solenoids. On the bottom graph you can see another voltage that is being developed on the solenoids. As this platter comes to a rest, the voltages drop to 0. Okay? Now I repeat this experiment. I start off with a higher speed. The EMF is, or a voltage is being developed across the first solenoid, and look at the shape of these voltages. It goes negative, then it goes positive. Positive, negative, negative, positive. And if you look at the bottom graph, as the magnet comes under the Hall sensor in its periodic motion, the Hall sensor shows a magnetic field. That magnetic field is pointing in some direction. Alright? It's pointing in the negative direction. And look at the top graph. If you observe the top graph, initially when the speed was large, the peak is sharper and it's taller. Look at the amplitude, 0.02. As the peak height diminishes, look at the amplitude, it's going down. This peak becomes broader and broader. So at high speeds, the peak is sharp, the voltage is large, and as the speed diminishes, the voltage drops because look at the amplitude, it's dropping, and the peak gets broader and broader. Whereas this magnetic field always remains at some amplitude 1.6, it remains fixed. Now what I'm going to do, look at the direction. This peak was pointing in the downward direction. If I invert the direction of this magnet, I just tilt it by 180 degrees. So I have a south pole or a north pole, an alternate pole now facing in the upward direction. So the field is now pointing in the opposite direction. Now if I repeat the experiment, this peak has gone up, which means that the magnetic field has changed its direction. Now this peak was previously negative followed by a positive. Now you have a positive followed by a negative. Likewise, the top graph has also shown a variation in the polarities of the EM of the voltages that are being developed. So I repeat this once more. I get stronger and stronger peaks at large rotation speeds, and then it gradually diminishes. But the magnet will come. Now what I would like to do, I would like to put magnets at different positions on this platter. Okay, and now I repeat the experiment. So for each magnet I get a negative and a positive lobe, two lobes of voltages, a negative voltage and a positive voltage for each magnet. Now I have many magnets placed at equal distances on this platter, and I get all kinds of peaks, and these magnets are all pointing in random directions. I have 5 or 6 magnets. I just place them in whatever directions I like. So these peaks are positive, negative, negative, positive, so they alternate and they reflect the direction of the magnetic fields. But due to each magnet, there is a negative side and a positive side. Look at these magnetic fields. They are positive, negative, positive, negative. So where is this voltage coming from? There is no battery connected to the solenoid. There is no current source connected to the solenoid, but it's picking up a voltage. And since there's a voltage, there is a current that is flowing through the solenoids. Because a voltage implies a current in a resistive circuit. Where is that current coming from? I haven't connected any power source. So the source of this voltage, of this EMF as we learn later, or there's a non-conservative electric field that is being picked up by these solenoids that exists inside these solenoids, which causes a current to flow, and that non-conservative electric field or non-coulombic field arises because of changing fluxes. If I place this magnet under a solenoid, now this magnet is just under a solenoid, the field is strong inside the solenoid, but it's non-changing, so there is no electrical voltage that is being picked up. So even though the field can be strong, there is no change in the field, there is no change in the flux. It does not create a non-coulombic electric field. This non-coulombic electric field is actually an EMF, as we'll learn later. So this is one demonstration. The other demonstration is also quite interesting. So what I have here is, and this will actually give me reason to describe the direction of this non-conservative electric field, non-coulombic electric field. And why do we have a minus sign in Faraday's law? In the next lecture, I'm going to talk about many examples, so don't you worry. Today I'm just giving you a motivation. Let me just stop this file. What I have here, what do I have here? Now this is I have two kinds of pipes here. Here. So this is a PVC pipe. It's an insulator, non-metal. The second pipe is a metal pipe. It's just ordinary mild, probably mild steel. It's conducting. And both of these are hollow from the inside. So what I have is a tiny spherical magnet. This is a spherical magnet, right? It's like a sphere, okay? But it's magnetized. It's a permanent magnet. It's a ferromagnet that has some remnant large magnetization. Now what I'm going to do, I'm going to make this magnet, if I just drop this magnet, it's going to fall down with the acceleration due to gravity. It's going to fall down. Nothing special about it. So I just drop this magnet through this PVC pipe, it's going to fall down. Nothing special about it. Now what I would like to do, remember this has a magnetic field. So it will create a magnetic flux. And that flux will pierce different areas. Now what I would like to do, I would like to take the same magnet and make it fall through this metal pipe. Okay, I take this magnet, it's hollow. There's nothing inside this pipe, right? It's just hollow. Okay, आप यहाँ देख सकते हैं. So I have this magnet and I drop it. I dropped it. It hasn't yet come out. Friction? Friction कहाँ से आ रही है? Air की friction वो तो इसके अंदर भी थी. Okay, let me do it once again. Just look at the speed. It's of course it's not decelerating or accelerating with g. Its speed is much smaller. It's not free fall, in other words. Just takes a good 5 or 6 seconds. I dropped it. And I'm waiting. Now let's try to actually have a close-up of this. There's no honey or no viscous medium inside this. It's just plain air inside. Ali, क्या हो रहा है? ये क्या होता है? Alright, ठीक. अब जरा इसको. Okay, I'm going to drop this magnet. You can see from a top view back to. Let me do it once. Now, which supernatural force, which deity is stopping this magnet from actually falling down due to gravity? All right. Can anyone come up with an explanation? Any explanation? Any explanation? हाथ उठा था यहाँ पे जी, आप बताएं.
When you drop that magnetic field that conductor was changing, current was producing that conductor, and for the production of that conductor, magnetic field in the opposite direction was produced. Then these two magnetic fields will counteract both with the next part.
Excellent. Excellent. So what's happening here is Faraday's law is at work here. This negative sign is at work here. Now, how do we explain this negative sign? Suppose I'm looking at this solenoid once again. And suppose the field is pointing outwards. Okay? So the current is flowing through the solenoid in this direction, I. And the field is pointing outwards, of course. Of course the field is being produced by some original current. That's the current to the solenoid. So this field is being it's pointing in the outward direction, and it's uniform inside the solenoid. Now suppose this current is increasing with time. Okay, so I have di by dt is positive, which means that with time the current is going up. Now what's happening to this field? This field is always in the outward direction, but it's increasing with time. So the flux is outwards and it's increasing with time. So the field is outwards. dB by dt is positive. It's the magnetic field is increasing with time, and since the field has a direction, this is out. It's out and increasing. Now if I were to find out the electric field produced due to this changing flux. Now this flux is through an area. That area is really this area. This is the flux through this area. Now the flux through this area is changing and it's increasing. If this area is outward, the flux is also positive and it's outward. Now if I were to find the Curly electric field at some point P, and this will be the same as all other points on this circle because of symmetry, there is no other possibility. And if you were to find out the direction of the Curly electric field, whether it's clockwise or anti-clockwise, what we would have to consider is what is called the Lenz's law. The Lenz's law states that if a non-coulombic electric field is produced, and if this were a conducting path for a charge, and if the charge would make a current because of the non-conservative electric field, whenever your electric field's charges move. So if the charge moves, and it moves in such a direction, such that the magnetic field that this induced motion of the charge produces opposes the direction of the change. Now the change is outwards and positive. So this charge, a hypothetical test charge here, would like to move in a direction so that it produces a magnetic field in the inward direction, so that it can oppose this stimulus. For that, the charge must flow in the clockwise direction. So the electric field that is produced, since we're talking about positive charges, the electric field is curly and it's clockwise. So this is the electric field that's produced here. How much is this electric field? Of course, the electric field here is going to be the same as the electric field here because of symmetry arguments. So if I use Faraday's law, and if this distance is small r, and if this cross-sectional area of the solenoid is capital R, then according to the left-hand side of Faraday's law, E, it's non-conservative, remember, or non-Coulombic, 2 pi R equals minus dV by dt of V dotted with dA Now this area is fixed. This is the total area under this dashed circle. But the magnetic field is only inside the yellow circle. There is no magnetic field here. So there is no flux that is outside the solenoid. So the flux through this area is 0. Remember, you have to take into account the entire area. But the field through this area is 0. There is only field inside this circle. So I can write this as minus dV by dt. This dA's integral is just this area, pi capital R square into B. So I take the derivative of this, okay? Since the field is always parallel to the area vectors inside this surface. So the surface is pointing outwards, the area vectors are pointing outwards, and the field is also pointing outwards. So the dot product gives you a cosine of theta, which is 1. So I take B multiplied by pi r squared. Now this is constant, pi r squared. So this equals minus pi r squared dV by dt. Now dV by dt is mu naught n di by dt. So this is the non-conservative, non-Coulombic electric field that's produced. And if I take 2 pi r to the other side, I will have an electric field non-Coulombic equals minus pi r squared mu naught n over 2 pi small r di by dt. This is the magnitude of the electric field that's produced. And this negative sign just is in full accordance with Lenz's law. Alright? Now if the field were actually, if this current were flowing like this, the field is still pointing outward. But now let's suppose that the current decreases with time. Now if this solenoidal current decreases with time, the field is still pointing outwards. dV by dt is now inwards, because the field was outward, but now the outward field is decreasing. So the change in magnetic field is into the plane of the black hole. So the field was pointing outwards, but now the outward pointing field is dropping, which means that the change is inwards. Now the change is inwards, which means that dV by dt is positive inside. The change in magnetic field is inside. With time, there is an extra field that's coming in somehow that is inward. So the change in the magnetic field is inside. Now the current, induced current due to an electric field will flow in such a way that this change is counteracted. So it tends to produce a magnetic field in the outward direction. And that magnetic field is produced when an induced current flows in the anti-clockwise sense, which means that the induced electric field or the non-Coulombic field is now curling in the anti-clockwise sense. If you have a scenario in which the solenoidal current is flowing in the clockwise direction, then the field is actually pointing due to the solenoid in the inverse direction. Now if this current actually increases with time, then the field inwards is increasing with time. So the induced current will be in such a direction so that it produces its own field that's outwards. That would mean that the electric field is going to curl like this, because this produces a field that's pointing outwards. if you have an inward pointing field that is decreasing with time, which means that the field is actually increasing in the outward direction, the induced EMF or the induced current will be in such a direction that it produces a field in the inward direction, and that necessitates a curly electric field that is in the clockwise sense. So this case is the same as this case. These two cases are the same as this case. Here the field is increasing in the outward direction. Here the field is also actually increasing in the outward direction because the field that's going in is decreasing. So really the field is increasing in the outward direction. So the change of the flux is counteracted. And in the last minute, I would just like to describe what's happening in this particular example. In this particular example, I have a metal pipe. Let's take a small section of this pipe. A magnet is falling through this pipe. It produces a flux. As this magnet approaches this section of wire, the flux through this wire is increasing with time. And when it's increasing with time, it must, an induced EMF or an induced non-conservative electric field must be produced, such that if charges were to flow due to that induced electric field, they will produce a field that's pointing in the upward direction. So on the outer periphery, a non-conservative electric field is going to be produced in this direction. It's going to wind around the surface of this section of metal pipe and it's going to produce currents. Now this is a conductor, so it can produce currents in response to a non-conservative electric field. Once an electric field is produced, currents can always flow. It doesn't matter for charges whether the field is conservative or Coulombic or non-Coulombic. Whenever there's electric field, currents can flow. So this induced current is called an eddy current. And it produces a magnetic field of its own that's pointing in the upward direction. So there's a diamagnetic effect. This dipole is pointing in the downward direction. This dipole is pointing in the upward direction. There's a repulsive force, and as a reason of which this magnet's downward motion is halted, and it just falls like the petal of a flower. Falls like, it cruises down slowly because of this induced EMF. Alright, we'll have more examples on this in the next lecture. Thank you very much. Ali, yeah, the battery.